This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Alright, let's get cracking in. So, on Monday we started using our row operations to solve systems of linear equations. So we're starting with linear equations like the one at the top here. And you can write them in matrix form, like the one at the bottom. And then you can only write the things that we really need to know about and put it in augmented form. I've got no space on this bench. Alright, you can write it in augmented form so it looks like this. And we're saving ourselves some time. We don't have to write the x1 and the x2 and the x3. And then you can do your row operations. And you can start finding the solutions to these equations. So what value of x1 and x2 and x3, or x and y and z, can you stick in these three equations so that they'll all be satisfied all at the same time? Okay? It's like saying when do two lines cross, or when do three planes meet, that kind of thing, in 3 dimensions. And remember I said normally we're not caring about geometry or hamburgers and chips. We're normally caring about something numerical, or something to do with radar, finding something at the bottom of the ocean. That's when you use these kind of techniques, okay? But we need to know what's going on. You don't want to do that kind of thing by hand with hundreds, so you just do it with 3 to start with, and then on we go. I was going to say something else, don't know what it was. Okay, so we started doing a bunch of examples, and we're part way through the examples. We've done these ones. So we've got a couple more to go, and then we'll talk about something else for a little bit as well. All right. Okay. Example 26. Find a solution, if it exists, to the following system of equations. Okay, so we can write this down in matrix form if we wanted to. It doesn't tell us to, so we're not going to, because we're a little bit lazy. But we can write this straight in augmented form, okay? So we're going to get all the important bits of information out, put it down in augmented form, that's all we need, and then we can figure out the solution from there. 2. Okay. Remember, if there's a 0, be careful where you put your 0, because I don't always write it so nicely that you can see exactly where the 0 is going, okay? So make sure you get your 0 in the right place if there's a 0. Okay, so normally you want to see a 1 in the top corner, so you can pivot on it. I'm not going to make that a 1, I'm going to get fractions, and these are all multiples of 2, so let's just leave it like that. So I'm going to do row 2 goes to row 2 plus row 1, because that's going to give me minus 2 plus 2, and it will put a 0 here, which is what I want. And the same for row 3 as well. 0, 2, 3, 5. Okay, so that first column almost looks how we want it. Normally you want a 1, but let's deal with that later. At least we've got the zeros. Okay, so now we're going to move to the second column. This 1 take 0 is 2, 1 take 1 is 0, 2 take 1 is 1, 3 take 2 is 1. Okay, row 3 goes to row 3, take 2 row 2s. Because then I get 0 take 0, that's good. 2 take away 2 of those. 3 take away 2 of those. 5 take away 2 of those. Okay, now if you want to, you can find the solution from there, right? you can see that that bottom row is telling us that x3, 1 times x3 is equal to 1. I can substitute that into the next one up, and it's telling me x2 plus x3 is 2, so I can figure out x2 from that, and I can keep going up. I'm going to do a couple more row operations, okay? Either way is fine. So. 2, 0, 0, 0. Okay. Now we can read the answer off of here. Now, when we come time to do eigenvalues and eigenvectors, which is going to be, I think, in week 4, when we come time to do eigenvalues and eigenvectors, we're going to be doing this kind of thing all the time. And there is one thing that I see students do a lot, and I do it too sometimes, so I'm telling you all about it so you can not do it, because it will... And it seems obvious, right? This one here, this row here is saying x1 equals 0. Yeah? This is where me and lots of students make mistakes, and they say x1 is equal to 1. It's not. It's equal to 0, and I don't know why we do it, but lots of people do it. So I'm telling you about it so you can be like conscious of it. x1 is equal to 0. Okay, so make sure you understand what's going on there. This one's telling you x2 is equal to 1 and x3 is equal to 1. Seems easy and obvious, but it's a really common mistake, so don't make that as well. Okay, let's write the answer down. Transpose is 0, 1, 1. Transpose, because we want it to be a column vector. Okay. Okay, what's going on here? Interpret the results geometrically. What are we starting with? In 3 dimensions, there are 3 planes. Beautiful. And what are they doing? Intersect. No. Yes, at one place. Who said that? Nobody who wants a lolly. All right, 3 planes meeting at a point. Meeting at the point. Which point are they meeting at? 0, 1, 1. Okay, that's the point they're meeting at. So in normal 3D geometry, 0, 1, 1. Okay. All right, does anyone want to ask any questions about that one? Yeah.
When you've done x1, x2, x3 like transpose, equals 0, 1 transpose, couldn't you just write that in column vectors straight away instead of having to write the T?
Yeah, sure. Yep. I don't like writing column vectors, so I write them as a row with the transpose. But yeah, you certainly can write them as columns and then you don't need a transpose. That's exactly right. Yep. Does anyone have any other questions? And I write, when it's a point, I guess what I normally do, when it's a point, I normally write it like a row vector with a transpose. But if it's a line, I write them as columns. And I don't know, that's just what I do. But certainly you can do it either way. Okay. All right. The next question we're not going to do because it doesn't show us anything that we haven't already done, but I will put the solution on the web, okay? So you'll be able to see it there, but we won't do that one. All right, the next one, 28. Whoops, that's the answers. Ha ha ha. All right, here we go. Yeah, I've got cheat notes, just to make sure. Not leading you astray? Okay. This one here. It's the same question again. Find the solution if it exists and interpret the results geometrically. Okay. So let's write it as augmented form. One, 0, minus 1. Make sure you get the 0 in the right place. Okay. I'm very kind and I've put a 1 here so we can pivot on this one. Bless you. Okay, row 2 goes to row 2 plus 2 row 1s. Minus 2 plus 2 gives us 0. Minus 2 plus 2, 4, minus 4, minus 6 plus 6, 4 plus 8. Bless you. Everyone's allergic to maths. 0. This one, take away that one. This one, take away that one. This one, take away that one. This is kind of weird. What are we going to do now? Leave it? Yeah, you should swap. Let's get this one down to the bottom. We could also divide by 2. That would be helpful. Okay. What's that telling us? Pardon? Who said that? No solution, yeah. You have to shout loud and stick your hand up so I can see who you are, and then you get a lolly. All right, there's no solutions here. This bottom row is telling us 0 plus 0 plus 0 is equal to 12. That doesn't happen. So row 3 is telling us, I'm just going to write this down because it's the first time we've seen it, I think. 0, 0, 0 equals 12. This can't happen, it's inconsistent. And there are no solutions. Okay. All right, if we're thinking about this geometrically, what's going on geometrically? Have a look carefully. Whoever gets the answer gets a lolly for this one. Who said that? Ah, you're smarty pants. 2 of them are parallel. The first 2, right? If you take the first one and multiply it by minus 2, the left-hand side is exactly the same. Right? And you can tell they're parallel and not the same because if you multiply the right-hand side by minus 2, you don't get the same answer, you get something different. So they're 2 planes oriented in the same way, but at a different height. Right, everyone watch out. Oh, that's pretty good. Okay, they're 2 planes that are parallel, planes 1 and 2. So if you were observant enough to see that before we did any work, you could write that answer down and say there's no solution, and that would be fine, and you wouldn't have to do any row operations. Wouldn't that be good? All right, does anyone want to ask any questions about that one? No? Okay. All right. Whole long string of examples. All right, find a solution if it exists to the following system of equations. Same question again. Okay, so we're going to do same row operations again. We're going to pivot on this top corner. Row 2. Okay, 4 minus 4 is 0. Bless you. Bless you. Everybody's got the sneezes today. 6 take 12. 15, take away 24. That's too hard. 9. Zero. 8, take away 14. 9, take away 21. 24, take away 42. That's too hard. 18. All right, these numbers look like they might be pretty nasty, and they're actually not, because we can divide. Here's a hint. If you're doing an assignment or the exam and you get really nasty questions and start getting 1/17 plus 1/3, da-da-da, chances are you've made a mistake. I'm not going to make you, I'm asking you to do these things by hand without a calculator. I go to great pains to make sure I give you nice numbers. Okay, so you might get a half or a third maybe, but you're not going to get things like, if we added up this wrong and got a 17 there, and you ended up dividing by 17 or something, we're not going to get that kind of stuff. Okay, if you've done that, if you've got that, you've probably made a mistake. So just go back and check. Minus a third. Minus 1/6. Okay, nearly there. One, take 0, 2, take 2, 3, take 4, 6, take 3, 6 I mean. Okay. Okay, the whole row of zeros at the bottom, whole row of zeros. That means that last row is telling us nothing anymore. So now we've only got the first 2 rows telling us something. So 2 pieces of information. And there are 3 things, 1, 2, 3, x1, x2, x3, that we don't know. So we're not going to have enough. This is where we introduce a parameter. You can introduce it for any of the 3, but normally there's one that's probably easier than the others. This time the easier one is x3, because x2 is related to x3 and x1 is related to x3 in the way that we've done the row operations. So that's the easiest one to pick. Okay. Let x3 equal t. x2 equals 3 minus 2t. Does anyone not see how I got that? Speak now, because we're going to use this heaps. Everyone's happy? If you're not happy but you don't want to put your hand up, make sure you come see me in the break or something. x1 equals 0 plus t. Okay. Now I can pick any value for t. Okay, doesn't matter which one. And there are infinite ones to choose from, so that means there are infinite number of solutions. Okay. Infinite solutions. Okay. Let's write them down a bit more tidily. Bless you. Equals, and I'm going to write them like a point plus a vector. Okay, so the point is going to be the parts that don't have anything to do with t. So here there's nothing. Here there's a 3, and here there's nothing. And the vector, because it can have any length, this t will change its length, is going to have a 1 and a minus 2 and a 1. Okay? Yeah?
It may seem like a silly question, but
No.
how do you know when to stop simplifying?
Stop simplifying here.
Yeah,
Is that what you mean?
yeah.
Okay, so this time I stopped when I got to reduced row echelon form. right? So you remember there's like 4 rules for reduced row echelon form. Any rows that have all zeros are at the bottom. The first number you come across should be a pivot. What else? Above and below the pivots have to be 0. And the pivots have to move to the right as you move down the rows, right? So that's reduced row echelon form, and so I stopped there. If you stopped, well, you don't want to stop here because you can see that's too hard to get any information from. I'll tell you the minimum. The minimum thing you need to do is get the bottom corner to have zeros. Okay? So I had to do this. I didn't have to make this a 0 though. But if I didn't make this a 0, I'd have more work to do here. Okay, so you can't, it's kind of like an equilibrium amount of work, right? You either do the work here or you do the work here, and you can't get out of it. It's one way or the other. But you're right, there's not a certain place that you have to stop. Yeah? Okay. All right. Okay, so the last bit of this question is interpret the results geometrically. So we started with 3 planes, and they're meeting what? How are they meeting? Everyone's quiet today. How are they meeting? They're not meeting at a point. They're meeting in a line. That's it. 3 planes meeting in a line. This is the line in 3 dimensions. Okay. And that's the line where they meet. All right, does anyone have any other questions? Yeah.
Could you write that line in the equivalent MX plus C form, but 3D?
Yeah, that's a good question, and the answer is no. In 3 dimensions, that's pretty much the easiest way to write a line. I guess in 2 dimensions, when you're doing it like y equals mx plus c, what you're doing is you're saying the plus c part is like a point. Start at this point, and I'm telling you a point on the y-axis, right? That's the intercept. And the mx, which we write first, is like then go along the line in a certain slope. Does that make sense? So you're starting at a point on the y-axis and you're going along the line a certain slope in each direction, and that's what gives you the line, right? And that's kind of exactly what this is doing. You've got x, y, and z, and then you're starting at the point, which is that first column vector. That's the point you're starting at. And then the second column vector is a vector that tells you the direction along which you travel. So here's the point in 3-dimensional space, and I'm telling you to travel along this line in some different distance. The different distance is t, right? And that's what will give you the line. So it's kind of equivalent to the y equals mx plus c, kind of. Like this is the point, and this is the kind of direction in which you travel. So this is like c, but it's not really mx because it's not an mx. This is just a direction to travel in, kind of thing. And that's just as simple as it gets, I'm afraid. It's not any better. Okay, does anyone have any other questions? All right, okay. There's a little part B to this question. Part B. Let's keep the equations there. Find the solution to the corresponding homogeneous equation. So don't forget, the corresponding homogeneous equation means take the interesting left-hand side part and just make the right-hand side 0. Okay, so let's write down the equations to start with. Oh. Just mindlessly copying them down. Okay, make the right-hand side 0. All right. Okay. Okay, so here's a system of linear equations. Write them down in augmented form. So pick out all the interesting information. Okay, and then we do our row operations. right? But this time we're not going to do row operations. We already did one of those. Bless you. On Monday, so we can do a little bit of a sneak because we've already done row operations on this. And if we do the same row operations on this side, we're just going to get 0 plus 0 minus 0, and they'll always stay at 0. Okay, so we can get the answer from the last question. If we do those same row operations that we did in part A, the left-hand side will look like this. And as I said, the right-hand side, you're just going to get 0 plus 0 minus 0, da-da-da. And they'll always stay at 0. And I said this last time, and I'll say it again, if you've got to do a system of equations and a homogeneous system, make sure you do the harder one first, because then you can do the homogeneous system just by writing the answer down. You can't go the other way. Okay, so do this one second. All right, we've still got to introduce a parameter, because we've lost our information here. x2 from this one, take that to the other side, minus 2x3, and x3 is a t. And x1, take this minus 1 to the other side, x1 is equal to x3, and x3 is equal to t. One minus 2, 1. When you do this, make sure you write down the answer. Don't leave it like this, all in the wrong order, and maybe mixed up in some other working. Always write down your answer nicely. And what else was I going to say? And the other thing is, when you go from here to here, be careful that it's in the other order. That's going to be important for eigenvalues and eigenvectors too. Okay? All right, you can pick any value for t, and there are infinite choices. So there are infinite solutions. Okay, 3 planes meeting in a line again. Through the origin this time, because there's no point at the start there. Okay, does anyone want to ask any questions about that one? Yeah.
Would our answers always have to be in vector equation form, or could we just leave it as x1 equals?
If you write x1 equals, x2 equals, x3, that's fine, but make sure you put them there in the right order, nicely down. Here's the answer. I'll tell you the thing I don't like first, and then you can say something else. A lot of people have a bit more extra working here, and they don't write it down again. So then we've got to go and search through the lines of working to see where the actual answers is, and that's not good. You can leave it like that, but write them in the right order at the bottom neatly. Yeah.
But when would we have to put it into vector equation? Would there be would it ask us specifically to do that?
Okay, so the reason I'm doing it so much now is because we're going to use this for eigenvalues and eigenvectors. Key point eigenvectors, and then we want to write them as vectors. So that's why I'm doing it so much now. Yep. Everyone's coming in from geology. I hope you had a good time. Was it fun? It was cold. Just in time for the complicated thing that we're going to do. You're the first of the two. Where did you go?
Kangaroo Creek Dam.
Where's that?
Gorge Road.
Ah, yeah. Okay. I think this is the last one we're going to do. All right. This is the last one of these that we're going to do, and it's a little bit different. And this is the one I said that if you're going on the geology excursion, make sure you pay attention in the lecture according to this part, so you're just in time. This one's a little bit different. See how we've got here, we've got a parameter. Well, let me point on here. Here we've got a parameter. This one here, and it comes up here as well. Okay? So now we've got to be a little bit extra careful. The other thing is the question is slightly different. Use row operations on the augmented matrix, we can do that, to find the values of k for which the system of equations has no solutions, infinitely many, or a unique solution. Okay? So remember, there are 3 things that can happen. These are the 3 things that can happen. Let's find out which values of k give those three different things, okay? When I put the past exams up, there's often a question that's similar to this one, okay? Pay attention. I haven't written this exam yet, so I don't know, but anyway. All right, put it in augmented form first. K squared take 14. K plus 2. Okay, don't be scared by the k's, just leave them there, they're just a normal number, and let's treat them as such. Okay, we're going to pivot on this one here. So row 2 will become row 2, take away 3 row 1s. That's easy. We've done lots of these. 1, 2, minus 3. This one plus 9. This one minus 12. Okay, row 3. Remember, we're aiming for zeros in that bottom corner, right? So we're going to do this one, turn this one into a 0. We want row 3, take away 4 row 1s. So 0. 1 take away 8 is minus 7. Okay, k squared take 14 plus 12. K squared take 2. Now k plus 2 take 16. Okay, just do it exactly the same. The k's just hang around and you can add the numbers up. Okay, so far so good. All right, the next, so we've done the first column, we've got that how we like. This one here, I'm not going to bother about reduced row echelon form. I'm just going to aim for the zeros here. I'm not even going to worry about that minus 7. I'm just going to go row 3 goes to row 3. What do we want? Take away row 2. This one, minus 7 minus minus 7, we want plus. 2 minuses? Yep. 0 minus 7, 14 minus 10. 0 minus 0. Minus 7 minus minus 7. This one minus 14. This one plus 10. Okay. Okay, so now I've got that bottom corner with all zeros in it, in the corner, those 3 zeros. That's what I want. When you're doing these questions, you can almost tell everything from this bottom line here most of the time. Not every time. Most of the time you can tell everything from the bottom line. So as long as you've got, you know, these 3 zeros here, you can see what's going on. Before we try and see what's going to go on, I'm just going to factorise this because I can see that I'm going to get something like this out, right? So that will help me. Actually, maybe I should. All right. Maybe that's not the reason I'm factorising. I'll tell you the reason I'm factorising. The reason I'm factorising is you can tell everything from the bottom line here, and whether there are all zeros or zeros on the left-hand side or zeros here or what's going on, okay? So what you want to know is when these little items here are going to be 0. This one's easy to tell because it's just going to be case 4. This one here, when you've got a quadratic, it's easier to tell when it's going to be 0 if you factorise it, okay? So that's why I'm going to factorise it, so I can know when it's going to be 0 or not. Now that's a pretty easy one. You can kind of see by looking at it anyway, but still. Oops, my line's a bit wonky. Okay, take 4. Okay. Okay, so now we've done our row operations. We've got zeros in the bottom corner, and now we can see easily just by looking when those other things are going to be 0. Okay, the first part, now we can answer the question. When does that have no solutions? What does the bottom row look like when there are no solutions? Think about it. We just did one before. Looks like 0, 0, 0, number. Beautiful. 0, 0, 0, number. Okay, so the bottom row will look like that. 0, 0, 0, and then you've got the line, and then you've got some number there. Okay, that's not 0. When's that going to happen? Minus 4. Who said that so loudly? Yes, you can have a lolly. When k is equal to minus 4... Oh, sorry. I need to eat my Weet-Bix. Okay. K equals minus 4. That's when it happens. Okay, because then you'll get 0, 0, 0, and minus 8. And that's when it's inconsistent. Okay. Okay, what's the bottom row look like when you get infinite solutions? Beautiful. 0, 0, 0, 0, all zeros, right? Zero, 0, 0, 0, and that happens when 4. You can have a lolly too. If k equals 4.
Is that only on the bottom row? Or does it happen in the second row?
Okay, so in this case there are no k's on the second row. So changing the value of k is not going to do anything to the second row. If you look, when I put past exams up, and I don't know, I haven't written the second assignment yet, but sometimes there'll be a k in the second row as well, and then you sometimes have to compare the first row and the second row. But next week we'll do a question similar to this again, and I'll show you an extra trick which can help you get around if it's a bit trickier. Yeah? But if it's just if you've just got k's in the bottom row, you can just look at the bottom row, that's it. Okay. I didn't give you a lolly, didn't I? Whoops, unique solution. Oh, there you go. You're having lunch. You can have that for dessert. Okay. What's going to happen? What values of k is going to give you a unique solution?
Not plus or minus 4.
Yes, you can have lolly too. Anything else except for not plus or minus 4. So k is not plus or minus 4. Here's a fancier way to write it. K is a member of the real numbers such that k is not plus or minus 4. That's the proper way to write it, but I'll take that. That's okay. Giving out lots today. All right, everyone watch out. Too far away. Oh! Okay. That's it. We answered all the question. When does those different 3 types of solutions happen? All right, does anybody want to ask any questions about that? Yes.
Is there ever a situation where, a unique solution could happen when k doesn't equal plus or minus 4, but then you sort of do more row operations if it's another number and it doesn't work out properly? Or?
Okay. No, it shouldn't. If you've done your row operations properly, that shouldn't happen. When I show you this extra trick next week, that will also make it easier to see from the start what might happen. So it's an extra trick that you do at the start, and then when you get to the end you kind of know what might happen, and then you just have to confirm it. But no, that would never happen. Yeah, no, it wouldn't happen. Does anyone have any other questions? No? Sometimes you have a case where you've got 2 different parameters, maybe like a R and a S, and the R will be on this side and the S will be on this side. And so you have to say, well, the R needs to make this one 0 and the S needs to make this one 0 or not 0, depending on what you're looking for. Okay, that's it. All right, that's all we're going to do of those. Oh, no, wait. All right, one little thing before we stop. Okay. These little matrices here, I've got a couple of questions, augmented matrices. Is it in reduced row echelon form? Can we find a solution? Or can we tell there are no solutions? And if there are solutions, can you tell what kind they are, unique or infinite? Okay. Is this one in reduced row echelon form? Yes. Reduced row echelon form. Is there going to be a solution?
Yes.
Yes. What kind of solution? Beautiful. Okay, and in this case, both of them are kind of linked with x3, so that's the one I would call the parameter. I'd say let x3 equal t. Okay, what about this one? Is this in reduced row echelon form? Yes. Is there a solution? Yes. What kind? Just one, that's right, unique. Okay, what about this one? Is this in reduced row echelon form? No. Okay, can we tell if there's a solution or not?
Yeah.
Yeah, what kind? Why do you say infinite? Because we're missing a row. No, we're not missing a row because there's 1, 2, 3, 1, 2, 3. Unique. Yeah, it's going to be unique, right? In this bottom row here, I could say that x3 is equal to 3. And in this row, I could use the x3 to figure out the x2. And in this row, I could use the x2 to figure out the x1. Okay, so there's just one, unique. What about this one? Is this in reduced row echelon form? Can you tell if it's got solutions? No, you can't really tell. You haven't done enough work. You've got to do more work for that one. So I guess you've got to at least get those 3 there to be zeros to be able to tell if it's got a solution or not. And if you go to reduced row echelon form, kind of depends on the question. Okay. Does anyone want to ask any questions? No? Okay. I'm going to do one little tiny quick thing, I think. Yes, and then we'll have a break. That it? Okay. All right, there's just one page on this, so we'll just do this quickly and then we'll have a break. All right, there are these things called check matrices, which I need to tell you about, and we'll never ever use them, but I have to tell you anyway. So I guess they kind of come in handy if you were doing something that had heaps of rows and maybe you were doing it with software or I don't know, something. If you have your matrix A and your little vector B that come from an equation that looks like this, if you stick an identity in here that's the right size, okay, it's got to have the same, it's got to be the same size as A, and you do a bunch of row operations, this A will turn into something else, the B will turn into something else, and at any time you can do this W thing times by your original A and you should get this little changed A here. And you can also do the W times the original B and you can get this little B thing here. Okay? Now if you keep going you'll end up getting A in reduced row echelon form and you'll get something here and you'll get the solution here if there's going to be a solution. Okay? So you can do this and then you can do this multiplication if you want to check what's going on. There you go, they exist. We're never going to use them. We're going to, I guess some of this might be of relevance when we talk about elementary matrices, which we'll do next week. But we're never going to use check matrices. Okay, all right, if nobody has a question, let's have a break. And I had a puzzle for you to do and I've left it in my office. So we're in for a boring 10 minutes, but maybe you want to stretch your legs at least. Okay. So let's start at 10 past.
I have 2 questions.
Yep.
Still recording. Is that possible if you...
That's exactly what I'm like now. I'm not actually. I'm really watching it. Don't take me. I'll get naked. I have no shame. So what did you do then? Just use.
I just read it now. Long way. Anyway, like right up halfway up my acre. Bus bottom down. I went and
I would just put it there, right? But you're not allowed to. Why? Maybe the answer is. One 10 million years, I'll take my chances. I'll be dead. I reckon I'll be dead in 10 million years. So I could be wrong. That's that problem. Yeah. I live in 741. Bricks and ground. You are? So you're good. You got some. You have waterfront property. See? Oh yeah. That's what I mean. It's slowly getting bigger and bigger. I'm waiting for you guys to. So you guys can fly. I got the tsunamis and shit that drown me. But you got nothing. You're in Kurdish. I know, poor real thoughts. Wait. It's super great and heavy. The type of road is like that deep underwater, all the shelves underwater, everything's underwater.
yeah, they used to.
Oh yeah, you've been here. The road used to be like, it's all like that. They used to be connected like a bit like and when it rained, ages ago. Yeah, like and when it rained, like, you know what public gyms do? All them down that far in the water. All the roads and everyone's just I got black light already. But my mate went to hospital with unwork. Nah, not really. I'm going to section.
The question is, No, 44. Like, still. That's the. It's pretty low, pretty calm. Yeah, so like this rock structure on this side, they're up the top there, they've got like heavy machinery, you can see they're cutting it all out, and they're trying to bring it down and a lot further away because the way that the rock structure is, they don't lock into each other and push back into the mountain. They sort of, they're in like sections like this, and so water can get in behind them and slide and come down onto the dam. And because if that goes, then it floods the city. So if this dam, it got broken, if any of this, like the dam is through here, so if any of that come down and cracks the dam, well, it wouldn't go around it. It would. This is the spillway, so that first photo you're seeing is from up there, and then that's where it goes down like a ski ramp, and that's the spillway again. That's down underneath, so that's under. Like they're extending all this back and making the water's in behind me. Yeah, directly behind. So there's the water there, and this is the dam facing on here. So they've already lifted it up. It's about maybe 4 meters, and they're going to go up another 5 meters again. Yeah, just in case, like that 1 in 10 year event that the water come over, and they can't control us. Yes. Well, they would have started filling up, so that's like the downside, and all the water's on this side. And then that's that base that they're trying to fix. And then all of this will come up higher and across. Yeah, this dude was like in a little basket, just like picking at the rocks to, yeah. Yes, that's the direct flow from the currents. So, yeah, it's pretty cool. But yeah, I think someone wants to ask a question about it later.
Nothing. Oh, well.
I saw that.
Yeah, I know. And then I'm sweating cheese.
Jack, what's going on out there? I was going to say, it sounds like someone's fighting this thing.
No, I'll start off with this. 3 and 2.
Okay, let's get cracking, shall we? I have nothing interesting to say because I left it in my office. Anyway, okay. Linearly independent vectors. Everybody prick your ears up because this is probably the first thing that you really haven't seen before. Okay, if you have a bunch of vectors, I can make a linear combination of them and it looks like that top equation there. Okay, so remember a linear combination of things just means add them together and you're allowed to put constants in the front. That's it. You can't square them, you can't multiply them with each other, you can't take the cosine of them, you can't do anything fancy. Add them together. The only extra thing you can do is put constants in the front. So those C's are just arbitrary constants. Okay? Okay, now consider this equation here that's on that second line there. So it's exactly the same. It's a linear combination. But I've said let's make a linear combination of them and we'll say it's equal to 0. By the way, that 0 should be a bold. It should be a vector, right? You're adding a bunch of vectors, you should get a vector. Okay, now let's think about it. If I have a bunch of vectors that have all got numbers in them, what kind of values of C can I put in that equation so that it's going to be true?
0.
Yeah, 0. That's an easy one, okay? I can put zeros in for all those C's and it's going to be 0. That's okay, that's a valid answer. Good. Okay, now here's the thing. If that's the only set of C's that you can find, if they are the only values of C that make that equation work, then that whole bunch of vectors all together as a collection are called linearly independent. Okay? And I'll tell you why. Let's say that there's a different answer where at least one of the C's is not 0. Okay? And here I'm going to pick C1, but you could pick any of them. If C1 was not 0, right, I could rearrange this equation here. I could put all the other vectors on the other side, like this, and then I can divide by C1 because it's just a number, it's just a constant, a scalar. Okay, and then I'll get something like this. And you can see here if I do that, I can write V1 as a function of all these other V's, these other vectors, so it's depending on those. So if there's at least one of the C's that's not 0, I can write this vector so that it depends on the others. And if it depends on the others, then the whole bunch of them together are called linearly dependent because it's depending on the others. Okay? So if you can do this, then they're linearly independent. Linearly dependent, sorry. They're linearly dependent because it depends on the others. If the only answer to this equation here is that all the C's are 0, then you can't rearrange it like this. And so they're called linearly independent. Okay? All right. Now, this is kind of really important because it's important for things like unit vectors. So when you're describing what's going on in 2 dimensions, 3 dimensions, whatever, the vectors that you use, you guys have done I, J and K, yeah, in physics? Okay. I and J and K, they're linearly independent. You can't make one in terms of the other, okay? They're not unique. You can choose a bunch of other vectors, okay? And so long as they're linearly independent, you can still do all the calculations that you need to do. It's just nastier, that's all. Okay. Let me just see when I want to say something. Okay, I'll say it in a minute. Okay. Right, here's another fancy word, a vector space. A vector space is a collection of vectors that can be formed by a linear combination of a set of basis vectors. Okay, let's see what that means. Basis vectors have to be linearly independent, so you have a bunch of vectors. You can't make one from a combination of the others, so they're linearly independent, and they can be called basis vectors. Now, if you make different combinations of those vectors, different linear combinations, you can make another vector. And all the different vectors that you can make by taking these different combinations of these basis vectors make up what's called a vector space. Okay? All right. So if you think about it, if you think about I and J and K, I can make a vector that's like 1, 2, 3 by taking 1 of the I's and 2 of the J's and 3 of the K's. I'll make a vector that's 1, 2, 3. And that vector is in the vector space that's formed by the I, J and K vectors. Now if you think about it, the I, J and K vectors, they're the unit vectors for 3 dimensions, right? So you can get anywhere in 3 dimensions with those 3 vectors, those 3 unit vectors. So 3-dimensional space is the vector space for the I, J and K vectors. Okay? What else? If you have a vector space and you have a set of basis vectors, if you add another vector to that set of basis vectors and the vector that you're adding came from the vector space, your vectors are no longer going to be linearly independent because you're adding one that you could have formed by a combination of the others. Does that make sense? Okay. All right. If you look at any vector space, the basis vectors are not unique. Okay, I can choose I and J and K for 3 dimensions, but as I said, I can choose lots of other things. So long as they're linearly independent, they still form a basis for the vector space, which is 3 dimensions. By the way, this little R3 that's here, this little R3 thingo, this R means real numbers, and when I put it to a power 3, it means all the real numbers in 3 dimensions. Okay, all the real numbers in 3 dimensions, so that's just 3-dimensional space. If you think about a vector space and you think about its basis vectors, if you count how many basis vectors it's got, that'll be the dimension of your space. Okay, so for 3 dimensions you use I and J and K. We need 3 of them, it's 3-dimensional. Okay, if you want 2 dimensions, you just use I and J normally. You can use lots of other things, but you normally just use I and J. And so your dimension is 2 dimensions. Okay? All right.
So the basis vectors, they don't have a scalar component in them? Or?
No, they don't have a scalar component in them. So, the basis vectors, they're just a vector. When you write a linear combination of them, you can put a scalar out the front, because a linear combination just means add them together. You're allowed to put constants out the front that are scalars. Does that make sense? Is that what you're asking? Yeah? Okay. Yeah.
Do these basis vectors need to be perpendicular?
Oh, that's a good question. Do the basis vectors need to be perpendicular? The answer is no. Okay, so if I are just looking at 2-dimensional space, if I have the normal vector that's the I vector, if I take a vector there, I can get everywhere in 2-dimensional space by adding these 2 vectors together. They don't need to be perpendicular. They also don't need to be of length 1. Okay, I'll tell you another fancy word. If you have a set of basis vectors and they're perpendicular, right, and they are of length 1, That's called an orthonormal basis. Okay, and I'll tell you why. In 2 dimensions, you talk about 2 lines being perpendicular. If you've got 3 dimensions and 2 lines are at right angles, they're called orthogonal. Okay, so orthogonal is the fancy word for perpendicular in more than 2 dimensions. So that's where the orth part comes from. And normal means of length 1. So orthonormal basis would be a basis of vectors, ortho, so that means they're perpendicular or orthogonal to each other, and normal means they've got length 1. Okay, so they don't have to be orthonormal to form a basis, but if you're doing calculations in space or in the real world, it's kind of handy to have them orthogonal and to have them normal. Okay, you can get bases that are, I'll tell you an interesting one. So a friend of mine does modelling for, they use this thing called a spiral separator to separate mineral ores from, separate the minerals that you want from something else. So you get this big spiral in like a helix, you crush up the rocks and you make it into a slurry like of water and rocks, and you make it go down the spiral, and then it comes out the bottom, and when it comes out the bottom, the bits that you want will be on one side of the little chute, and the bits that you don't want will be on the other side of the chute. So she does a lot of modelling to see about what shape they should be and all that kind of stuff, what kind of slope they should have going down, that kind of thing. The coordinate system that she uses is not orthogonal. It's a special kind of coordinate system, so it's not spherical, it's not cylindrical, it's not the normal Eulerian one, it's a helical, it's called a helical coordinate system, and then they're not orthonormal, and then the differential equations are a nightmare, but that's the best way to do it. So there you go, there's a long answer to that question. Okay. Alright, let's think of some examples. So, here's the first example. This little vector here forms a basis for the set of vectors which lie on the x-axis. So if you think of 3 dimensions, you normally put z going up, and x going forward and y going this way. So if you had only that vector, you could get everywhere on the x-axis forward by using a positive number and backwards by using a negative number. Okay? So that little vector is just a basis for the x-axis. Alright, next one. Okay, these 2 little vectors form a basis for r squared, so that's the normal I and j in 2 dimensions. They're linearly independent, okay, because I can't make one of them using the other one. You can just see that just by looking. And you can get everywhere in the xy plane using those 2 vectors. So those 2 little vectors form a basis for r squared, okay, the real numbers in 2 dimensions. Okay, here's another one. Consider the set, this one's like I, j and k, right? So we can get everywhere in 3 dimensions using those vectors. You can see just by looking that you can't make one by a combination of the others, okay? So they are a good basis for the real numbers in 3 dimensions. They span R3, that's the proper way of saying it, and they're linearly independent. Okay. All right. Here's one. The set of basis vectors for a vector space is not unique, so I can even show you an example. If you think about 2 dimensions, right, normally you would just have I and j, but if you have 1 and 1 and -1 and 1, these 2 things form a basis for r squared. I can get anywhere in r squared just using these ones. Okay, and if you think about it, you could have, let's see, if you have 2 and 4, okay, I would take, what would I take? 3 of the first one, and I would do 1 of the second one, okay, and then I'm here. And you can put any numbers here, and you'll be able to find a linear combination here. So pick a number here, and pick a number here, and you'll be able to get anywhere in 2-dimensional space. Okay. You can also see pretty quickly by looking that these 2 vectors are not linearly dependent, because I can't make this one by timesing this one by a constant. Okay? Yes?
What's up with the 1 and 1? Is that an and or a half?
That's an and. Is that right? There we go. That's probably just worse than that. Okay, that's an and, okay? So I can take this one, and that will be a vector space for r squared. All right, does anybody else have any other questions so far? No? Okay. All right, what else did I want to say? Okay. All right, so those three vectors that are at the top of this page are the normal I and J and K vectors. So they're going to form a basis for three-dimensional space, right? Now it's easy to see just by looking that those three are linearly independent because I can pick any one of the three and I can't make that one by a linear combination of the other two. Okay, that's easy to see. Okay, the question comes when you think about something harder than that, like I guess these ones it's quite easy to see too, but as soon as you get three vectors in three-dimensional space, it's much harder to see whether or not they're linearly independent. Okay, now the question that we're going to worry about in this course is how do you tell whether three vectors are linearly independent? Okay, if it's harder than this kind of thing. And that's what we're looking at here. Okay. Right, so let's think about this. If we have a bunch of vectors, and I'm going to call them all u's, right, here they are here. Here's my u vectors. I've made a linear combination of them, so I've added them together, and the only fancy thing I'm allowed to do is multiply them by constants. So that's what I've done. This should be bold as well, by the way. Okay, now remember, if they're going to be linearly independent, that means I can't rearrange it, then the only solution to that thing must be that all the c's have to be 0. No other choices. Okay, the c's have to all be 0, and that's the only way this equation is satisfied. Okay, now let's have a look at what this means. If I have, what have I got? I've got C1 times this U1, okay, and they're column vectors because that's how they're supposed to be, plus C2 times by U2 plus da-da-da-da, plus Cm, did I use M? N. Plus Cn times by Un, that's a vector, has to be equal to 0. Okay, so that's a vector of zeros there. Okay, now the question is the only answer that these c's have to be all 0? If I expand this a little bit more, I can write something like, well, this C1 is going to be times by each little guy sitting in this vector, right? So the first one I'm going to call U11, that's going to be the little top one. The first dude in this little vector is going to be a U12, so that tells me it's the first one in the vector and it's in the second vector. Plus, this is why that indice thing was important last week. Oops, Cn. And I haven't even got a thing today. Not allowed to make any mistakes. I'll make another one. Okay, equals 0. So if I read across the first line of this thing here, this is what the equation will look like. Okay? If I read across the second line of that, I'm going to get the second line in the first vector. Oh, man. C2U22 plus da-da-da-da plus CNU2N. Okay, equals 0. And I can read across every line here and get a bunch of things like this. Okay, now I've given you the vectors and I'm going to ask you, are they linearly independent? If I've given you the vectors, it means you know this thing and you know this thing and this thing. So you know all these u's, right? And the question you have to answer is the only answer going to be all the c's have to be 0? So these are the things you don't know, right? And you don't know them here, but they're the same values. Okay, now that looks kind of like these, right? I've got something I don't know, something I do know, something I don't know, something I do know, and the thing I don't know gets repeated down here. Okay, so this is exactly the same, but this time I've got the letters swapped around from what's up there. Okay, so I could rewrite this like a matrix. The things that I do know are these u's, and they are going to go in a big, that's a capital U, they're going to go in a big matrix, okay, and these are going to be the columns of the matrix because it's just like writing the matrix form. The things I don't know are these C values, and they're in a column vector, okay, because we write them in a column vector. And we write them in a column vector because remember when you do AX equals B, you have to pluck this out as a column vector so the matrix multiplication works. So that's what you do here. And then on the right hand side you've got 0. Okay, and this looks like something we know what to do with. Okay, and remember the question we're asking is the only choice that these have to be 0? Okay, if the only choice is that these have to be 0, then they're linearly independent. Okay, there, okay, and that's what I've got here. Okay, the set of equations can be written like this. So here's a vector that we don't know. Here's all the, this is the different C's. Here's this matrix made up of the vectors that I've given you. Okay, and you have to ask, what do we know about C from that? Okay. Does anyone want to ask any questions so far? No? Okay. So here is what you do. You put the vectors that you're wondering about and you put them into the matrix as a bunch of columns, okay? And that's because they come in like this. These are columns, so in the system of equations they come into the augmented matrix like this, okay? Okay, do a bunch of row operations and reduce the matrix to reduced row echelon form. Now, if you get the identity, right, if we write them in augmented form, right, this side is going to be all zeros, and this side here is going to be the vectors that I've given you. If you go do your row operations, and if you get the identity, okay, remember the things we don't know are the C's. This is going to tell you C1 equals 0, C2 equals 0, C3 equals 0, and that's the only choice. Okay? So you reduce it to reduced row echelon form. If you get the identity, then the only solution is the trivial one, where everything is 0. And then the vectors have to be linearly independent. Okay, because you can't have a non-zero C to rearrange that equation. Okay, it's actually a little bit easier than that. If you can do this, we're going to talk more about this next week as well. If you can do this with your row operations, it means the matrix is invertible. Okay, and don't forget, if it's invertible, the determinant's not equal to 0. So why don't we just find the determinant instead of doing the row operations? Okay, so that's what this first one says. If it's square, it means it's in, and you can get it down to the identity, it means it's invertible, so let's just find the determinant instead. If it's a different size and it's not square, then you have to do your row operations and see if you get this at the top and then a bunch of zeros at the bottom. Okay, and then you know that they're linearly independent. All right, we're going to do a couple of examples. Does anyone want to ask any questions? No? Okay. What do I need to do? Okay. Okay, so here are my 3 vectors, 1 and 2 and 3, and you can see by looking at them, well, I should say you can't see by looking at them if they're linearly independent or not. Okay, it's really hard. I mean, you can sit there for a while and think, what if I take one of those and 2 of those, then I'll get that right. If I take one of those and 2 of those, well, then that one's wrong. And you can keep trying and trying to see if you can get it, but you'll be there for a little while to make sure. So you have to do it properly. So the question is, U, that's a capital U, times by this vector of unknowns equals 0. So what solutions can we find to this little equation when this capital U is equal to And I'm going to get these vectors and I'll put them in as the columns, okay, because this is where they come from. 1, 1, 1, 0, minus 1, minus 1, 2. Okay, so what solutions can we find for those C's where U, this big fat matrix, is made up of column vectors of the vectors that we're interested in? Okay, now this is a square one, so we're in this case here. So we can do this row operations to get to here, and if we find the identity, then the only answer is all the C's have to be 0. So we can do that. If we're too lazy to do a row operation, like me, this will only happen if the determinant is not equal to 0. So that's what we're going to do. We're going to find the determinant. One minus 1. Okay. All right, we also like to save ourselves work, so let's just do it by the third row. Oops, can't even spell. By the third row. Equals plus minus plus times by the determinant of what is left. Plus minus plus minus, plus minus plus minus plus. Okay. Be really careful with your signs when you're finding determinants, and be really careful with your brackets. It's not quite so important here, but we're going to do determinants with parameters eventually, and then it becomes really important. Be very careful with your signs and your brackets. So this looks like 2, and this one looks like 4, 6. Okay, the determinant's not equal to 0. What does that mean? Let's write it down. So the determinant is not equal to 0.
So that's an equal.
That's exactly right. That's the very next thing I'm going to write down. Therefore, U minus 1 exists. Okay. If U minus 1 exists, then there's a unique solution. A unique solution, I should say this, 2 U C equals 0. Okay, there's a unique solution to this little matrix equation. Now we know, because it's homogeneous, we know that one of the solutions is that all the C's are 0, right? So, but okay, now if the trivial solution exists and there's only one solution, that's the only choice. Okay, so that's where we get our answer from. Is the only one. The trivial solution is the only one. That's the only choice we can have. Let me go back to here. Now, if the trivial solution is the only one we can have, so to make this true, the only thing we can have is all the C's are 0. If all the C's are 0, then there's not one where you can choose to do this thing, because we don't want to do 1 divided by 0, right? So you can't do this. So you can't write 1 in terms of the others. So 1 can't depend on the others. So then all of them together are called linearly independent. Okay? Okay, linearly independent because they don't depend on each other. Okay, does anybody want to ask any questions about that one? Yeah.
With the trivial solution and
Yeah. Okay, good question. So because the right-hand side is always 0, because of this is a vector, right? It should be bold. Because it's all zeros on the right-hand side, you can see that one answer is always going to be C, all the C's are 0. Yeah. So if there's only one, and you know that one of them is a trivial one, that's it, that's the only one. Yeah. Does anyone have any other questions? No? All right, we're going to do one more example. All right. Okay. By the way, if you think about the last example, you can't tell just by looking at them that you can't make one out of the others. Okay, you can sit there all day and try, and now you know you're never going to get there. Okay, what about this one? If you just look at them, okay, you can't tell by looking at them that one can or can't be made as a combination of the others. So, okay, so the question is, what solutions I'm going to call it A this time because my vectors are called A's, so I'm going to call it A, times by this vector of constants, which we don't know, is equal to 0. And we better say what A is. When A is equal to, and I'm going to put them in as the columns, and you put them in as the columns because they're column vectors, and when you write the linear system of equations out, they turn into columns. Okay? So 2 minus 1, 3. Okay, this one's a bit harder. There's no easy way to do this, we just have to do it. Okay, but because it's square, we don't have to do the row operations at least. We can just do the determinant, okay? Because we know if the determinant is not 0, we're going to get this, okay? All right. Yep, let's just do it by the first row. And remember I said when you're doing determinants, write this out because it's going to help you and it helps us as well when we're marking stuff, okay, to know which way you did it. So plus minus 8 plus minus plus. By the way, I had my tute yesterday and there was a couple of people in my tute that have done determinants at school and they've done them slightly differently. They've done it by adding writing the columns out again next to it, and then you don't need the checkerboard thing. If that's the way you learn how to do determinants, that's perfectly fine. It's exactly equivalent. It's a group theory thing about the ordering of the columns. So if that's the way you do determinants, just stick with that, that's fine, okay? I'm going to keep doing this way, but you do them whichever way you like. That's fine. Okay. Pardon? Plus, minus, plus, plus, minus. So it should be minus, minus. Yeah, and then it will turn into plus. Yeah. So 28 minus 72, minus 7, minus 18, 12, minus 12. That's nice. Okay. Okay. So this time the determinant equals 0. All right. Of course that's going to happen because I'm going to give an example each way, right? Okay. So let's write down what that means. The determinant is equal to 0. Okay, that means the reduced row echelon form is not the identity. Okay. If it's not the identity, it means that you're going to get some numbers somewhere else, and this one can't be a 1, it's got to be a 0. Right? This one down here. If this one is a 0, and then maybe because you couldn't pivot on this column, maybe you've got some numbers there. Okay? And remember, that's when we introduce a parameter, and the parameter can have any value, so there's infinite solutions, so there's more than just the 1. Okay? So, we already know that the trivial solution exists. Okay, we know that because if you look at this, you can see that you can just put all the C's being 0 and that one's true. So we know the trivial solution exists. And more exist too. Infinite solutions. Sorry, is my writing getting messy? More solutions exist than just the 1 because there are infinite solutions. Okay, so there's not just the trivial solution. That means you can rearrange it. Whoops, rearrange to make one vector in terms of the others. Okay, so something with a U1 and a U2 there. Oh, we've got A's, sorry. So A3, you could write that in terms of A1 and A2 somehow. And then this one will depend on the others. So then as a whole set, you call them linearly dependent. Linearly dependent with an E, not with an A. Linearly dependent vectors. Okay, does anyone want to ask any questions about that one? So if it's square, you can find the determinant, and from that you can tell what kind of solutions it can have, and from that you can tell if it's linearly independent or dependent. All right. Where are we up to? Okay. All right, so we just did those two examples, and there's a little note at the bottom here. If the matrix U can be reduced to the identity matrix, then one thing that you can say is you can say it's a row equivalent to the identity. Row equivalent to the identity. Now, if we turn this back, I haven't got my little rubber, so I can't do it. If we turn this back into the identity here, right? Now, if you look at, you know how we got this part of the matrix here by putting the columns in the vectors? If you have a look at the columns of this, they're just like I and J and K, right? The columns of the identity are just like I and J and K, so it's row equivalent to the I, J and K ones, okay? So it's row equivalent to the identity, they're the unit vectors, and that means that the vectors that you're worried about, the more complicated ones, can also be a basis for R3 or whatever dimension you're dealing in, okay? All right, does anyone want to ask any questions? No? All right, I think our brains have had enough for today. That's it, let's have an early minute. Have a nice weekend.